And we're underway. All right, so you guys all got the email I sent out, is that right? Okay, good. Exam is going to be next Wednesday. We should finish up everything today, but just in case I don't, I left Monday open for me just to cover any remaining parts. As far as I'm concerned, for the exam, we will not do a combustion reaction. I'll cover that afterwards. I think I might have told you guys that. So anyway, that's what's going to happen today. And let's see. Quizzes. Okay, you can look at me. It's all right. Quizzes, I'll get them up this weekend. Okay, they won't be bad. A couple of 5-point quizzes, you know, for chapters 2 and 3. I meant to get them up earlier, and it's kind of flew by, and I hadn't done it yet. So, what? Well, what do I look like? I'm slowly getting my energy back. Yesterday I was just feeling totally, I was back at school, the cough drops and my cough medication is working very well. Saw the doctor, he said everything is cool. But anyway, energy thing isn't quite back up where it should be. So if I seem a little bit sluggish or whatever, or irritable, it's just I'm getting over something right now. But also, I am not contagious, so if people come to my office, you don't have to wear a mask or anything, unless you're going to hold me up. But other than that, don't worry about it. All right, do we have questions here? Well, that is working well today. Do we have questions at all? No? Okay, well, let's see. Last class, we ended with balancing equations. Okay? And just to kind of, as a little warm-up here, could somebody remind us what is the need to balance a chemical equation? Why do we have to? Besides it being chemistry and it gives us something to do. Yeah? Conservation of mass. Or as I like to put it when it comes to balancing equations, conservation of atoms. Think of it that way. That's why we're looking at one hydrogen here, one hydrogen there, whatever. Okay? We have to account for all atoms, make sure that nothing is gained or lost. We're lost. We're not telling the chemical reaction what to do. We're kind of discovering things about the chemical reaction. And it's this deal of conservation of mass that leads us to balancing to make sure they have equal numbers. And remember, we never touch subscripts, okay? Never touch them. If we do, basically, we're redefining the reaction. We're putting different components together, okay? Whatever we state is in the chemical reaction, we have to stick with that all the way. So we just balance the chemical equation by basically adding more reactants or products, whatever is needed to do it. Okay? So any questions about that part? All right? Well, what I'm going to do now is, in fact, I think I might have touched on this right before the end, but let's go back to one of them that we did the other day, where we had the nitrogen and the hydrogen going to ammonia. Okay, we're going to have 2 here, and we're going to have 3 here. Okay, to have a balanced chemical equation. All right, now, first of all, I'm going to point something out to you. Next year, when you get to Gen Chem 2, you're going to see a reaction. In fact, you'll probably see this reaction. We get to equilibrium. You'll have 3 chapters on equilibrium. And when you get to equilibrium, you're going to see this. Okay? It's an equilibrium reaction. Now, I just want to point that out because I don't want you looking at your book saying, I guess Dr. Mundell doesn't know what the heck he's doing. Now, what I'm doing is I'm taking it because it's a nice, simple reaction. And I'm only talking about the forward reaction for the sake of discussion. Okay? But believe me, I recognize fully that it is an equilibrium reaction. In other words, you have a forward and reverse reaction going at the exact same rates. And the concentration of reactants and products are constant. And that's something that's going to be drilled into your head in the spring. All right? All right, so we have this reaction here. Now, the thing is, how can we interpret the coefficients of that balanced equation? Anybody remember that? 2 ways. I talked about this, didn't I? Dr. Goganea, did I? Oh, for Lord's sake, did I rush through this? Okay, well, let's do it. Okay, well, I'll call it a review. You guys sit there and take notes. What can I say? Okay. It's Friday. Let's be friendly. Okay, and also I have a just cold. Okay. Well, what does this represent? 1 what? molecule? Yeah, 1 molecule of nitrogen. I'm sorry, usually I do this just as I'm getting into this, and I guess I rushed through it. Okay, this is going to be 1 molecule of nitrogen. It's going to be 3 molecules of hydrogen and 2 molecules of ammonia. And that's fine, okay? You'll interpret balanced equations this way, balanced chemical equations. You'll interpret them this way when you get to kinetics next spring. Okay, you'll actually look on the molecular level, the atomic level, whatever, and see how things react. However, on the laboratory scale, it's totally impractical to talk about 1 molecule this and 2 molecules of that. Okay, we have to have handfuls of molecules, okay, so we can actually have things that we can handle and observe. So what we say is, we'll say 1 mole of molecules. Okay? Here we're going to say 3 moles of molecules. And here we're going to say 2 moles of molecules. Okay? We could say dozen, but that's totally inappropriate. I mean, it's inappropriate in the fact that you're not going to see a dozen molecules of this reactant, 2 dozen molecules of that in your normal everyday chemistry laboratory. But you can observe moles of molecules. Okay? I mean, you guys are all right with the idea of moles now, right? You okay with that concept? That's an appropriate unit of counting, if you will. Okay? So now we're going to interpret this as 1 mole of nitrogen, 3 moles of hydrogen, 2 moles of ammonia. Okay, the balanced chemical equation will be according to not molecules, but moles of molecules. Okay, now we have something that we can work with. All right, so what we have here is a ratio of 1 to 3 to 2. For this particular balanced equation, we are locked into that ratio of 1 to 3 to 2. Okay? And by being locked in, if I were to say, if you have 5 moles of nitrogen, how many moles of hydrogen will you need? Don't have to think about it, right? You can do it by inspection. We're locked into that ratio of 1 to 3 for reactants and 2 for the product. Okay, we can do this stuff in our heads. If I were to say, oh, here's a term I want to introduce to you now. How about, I'll put it this way, 5 moles of nitrogen react. How's my camera, by the way? Is my camera crew keeping an eye on this for me? No? Okay. I'll have to get a whole new crew. Okay. 5 moles of nitrogen react with excess hydrogen. Okay? I want you to pay attention to that term excess, because what I'm saying here is you got enough hydrogen, you don't have to worry about it. In fact, you'll have hydrogen left over. And this is a concept later in today's lecture we're going to come back to when we talk about limiting reactants. Okay? So when I say with excess hydrogen, in other words, just look at this number. Don't worry about if you have enough hydrogen. You have enough hydrogen and more. Okay? Okay, 5 moles of nitrogen react with excess hydrogen to yield how many moles of ammonia? And the answer is 10. What do you think? How many guys say 10? I think we're safe. Okay, 10. And how many guys weren't even paying attention? Raise your hands. There you go. I like your truthfulness. Okay, 5 extra points. All right. So those are big earphones you got there, buddy. What, are you flying a helicopter after school? Chopper. There's a parking space on West 15th Street. Got to have some fun once in a while on this job. Okay, so the answer is 10. All right. So does anybody have any problem with what we're doing right now? I shouldn't say any problems. Do you have any questions? Does everybody understand it? If you don't, this is a good time to raise your hand, especially since we have an exam next Wednesday. Everybody's all right? Oh, question, yes. The 10? Okay, well, that's what I'm here for. Let me. 5 moles of nitrogen, okay? Right? Right there. Okay, we got 5 moles of nitrogen here. Now, you can see, what is the ratio of nitrogen to ammonia? 1 to 2, right? Now, if I said, if I were to reword this, and say, you have 5 moles of nitrogen and enough hydrogen for the reaction. How's that sound? And that would be actually 15, right? Because it's a 1 to 3. Okay, so instead of saying 15, I just say you got 5 moles of nitrogen, and it reacts with enough hydrogen for the reaction. So you're okay with that, right? Now, with that said, you see why we got 10 moles of ammonia. Okay, now, what I wanted to show you was, we're going to, in a little while today, if we can get to it, hopefully, we'll be using the term excess. Like, instead of saying you have just enough, hydrogen, I'm going to say it's an excess hydrogen. In other words, we just flooded it with hydrogen. Don't worry about the hydrogen. You'll have a lot of hydrogen left over. Okay? So that's all I'm saying. And I introduced it just to kind of get you used to this idea. So when I get to this next part, you'll kind of flow into it. Now, do you have any more questions, or is that okay? Okay, if you do, let me know. Anybody else? Ask the questions. That's what I'm here for. Okay? All right, so let's see. From there, let's do some calculations. Now, the book, I'll be quite frank. I think I mentioned this before. I'm not crazy about this chapter. I think I like to do things in a different sequence, and there's also some things I think he goes into. He has a different approach to it, which I find might be a little confusing. But please read the book and see what you think. But look at my stuff first and see if what I say works for you. Just do that. Okay? So anyway, that being said, I'm going to work at this equation just for the sake of continuity throughout this lecture today. Wow, got to work fast. All right, so instead of doing something that is just kind of, look at the board and tell me what the answer is, how about if I were to say, given 1.73 moles of nitrogen, how many moles of hydrogen will be needed? Okay, and you know what I'm talking about. It's in regard to this reaction here. Okay, now before we could just look and say, 5 times 1, 5 times 3. Okay, now you look at this, and you can probably still work it out, but what I'd like to do is show you how to set the problems up using the balanced equation to get your conversion factor. Okay? Anyway, let's get into it. You can see here we have 1.73 moles of nitrogen. We go way back. This is our given unit. Okay, the unit we don't know about is moles of hydrogen. So right there we can see it has the makings for putting together conversion factor is what I'm trying to say. So now to do this type of problem, we have to have a properly balanced equation. Okay? And what we're going to do is we're going to just look here. In this case, we're going to be interrelating 1 mole of nitrogen to 3 moles of hydrogen. Okay? So now we go to the balanced chemical equation. Okay, so we have 1.73, am I on camera, by the way? Yes. All right, let me bring that just a little bit here. Okay, 1.73 moles of nitrogen times, now we want moles of nitrogen to cancel out. We want our answer to be moles of hydrogen. We look over here, it's 1 mole of nitrogen to 3 moles of hydrogen. Okay, so let's see, what are we going to have here? We're going to have 9, then we're going to have 21, carry 2, we're going to have 3, 5. 5.19, am I correct? Yeah, not bad for a Friday. Okay, so that's going to be moles of hydrogen are going to be needed. It's that simple. Okay, going back to the balanced chemical equation. Now, to do these, we're going to call these, let me see, let me move over here just a touch. Or I'll tell you what, you just copy this while I write over here. This first thing's going to be called a mole. Just a second. I said I'm coming over here, then I'm going to move it over. I don't want people to have time to copy this first. But thank you anyway. Okay, these are going to be called mole to mole. Where is it? It's up here. There it is. Mole to mole conversions. Okay, and the mole to mole conversions are based on a balanced chemical reaction. Or I should say balanced chemical equation to make it proper. Balanced chemical equation. Let me put this down here. Camera, how's that? All right, so get that down. Let's do something with it. I'm going to put this board up, put another board down. Hope you guys can hear me sniffle through the microphone. Something you have to look out for when you have a microphone, or noises you make, grumbling, whatever. All right, let's see, just do that. That should be good. Okay. So let's see, going back to the equation, I'll put it right here again. Oop, what am I doing? Okay, rather inverted the reactants, but it's still the same equation. Okay, now we can use this mole-to-mole conversion to, let's say, given so much reactant, how much product do we get? Or, if we want so much product, how much reactant should we use? Or, given so much reactant, how much of the other reactant do we need? In other words, we can use it all over this balanced chemical equation, the mole-to-mole conversion. Now, let's go back to this problem here. It says, given 1.73 moles of nitrogen, how many moles of hydrogen will be needed? Okay, let's, I tell you what I want to do right now is I want to switch to the product. So let's just do a product for the heck of it. Okay, I'll say given, let's say 37.2 grams of hydrogen. Okay, how many moles of ammonia are produced? Okay, let's take this apart real quick. Bless you. All right. Now I've switched from going from one reactant to the other reactant to product. Now, when you see this kind of problem like this, we're going by given so much reactant of this, how much product will we get? We assume that, in this case, the nitrogen is in excess. In fact, let me write that in here so we have that. Okay? I'll say assume nitrogen is in excess. Okay? In other words, you have enough nitrogen, don't worry about it. All right? Excuse me. Okay, now we're starting with grams. Can we go directly from grams on one side to moles on the other? Can we do that? No, because the chemical equation is balanced in moles. In fact, I'm going to show you a little something after we get to the next part here. But for right now, the first thing we have to do is convert moles of, in this case, moles of hydrogen to moles. Excuse me, I am so sorry. Sometimes I start rushing here trying to get through and I kind of I'm like a page ahead of what I'm supposed to be saying. Grams of hydrogen to moles of hydrogen. Okay? Grams of hydrogen to moles of hydrogen. Okay, the mole-to-mole conversion is the heart of these stoichiometric problems. We always have to go to moles at the center. Now, sometimes we will start with grams. We start with grams, we've got to convert them to moles, then do the mole-to-mole conversion. Okay? Is everybody following me right now? Okay? If there's questions, ask me, because I can. If you have a question, the rest of the crowd, there's other people who might have the same question. So, do you have a question about something? No, if you could share it with me, then I can share it with the class. If you have a question about something. No, never mind. People are just going back and forth, asking, pointing at the board. If you're having that much trouble, you ask me. I'll be glad to clear it up for you, and other people can hear the question too. Anyway, on with the show. All right, so to start this problem here, we're going to have grams hydrogen. We're going to convert that to moles hydrogen. This is the first step. This is going to be step 1. Camera. Thank you. Just a second. Let me get this up here and I'll put the camera on. 37.2 grams of hydrogen. Now, how far off is it here? How's that? Better? Okay. Now to do this conversion, okay, what's our conversion factor going to look like? Any thoughts? What'd you say? Yeah, but this is H2, right? So, okay, it's H2, but fine. Okay, when grams of hydrogen to cancel out, and we want moles of hydrogen to stay in. So, let's just say 202. How's that sound? Is that all right for right now? Let's see, how far out does our book take it? 01, yeah. Okay, 202. Does everybody know why that's 2.02? Because it's H2, okay? It's not H, it's H2. Okay, so let's put that in there. And let's get this. I'll do the calculation. Hopefully my head is nice and clear today. Okay. I come up with 18.4 moles of hydrogen. You guys agree with that? Really, I can easily make mistakes, as you know. Okay? Anyway, got 18.4 moles of hydrogen. Okay, now the next thing we're going to do is convert to moles of nitrogen. This will be step 2. So we're going to get 18.4 moles of hydrogen times, now what's our conversion factor going to look like now? Oh, I'm sorry. Did I say hydrogen? I meant to say ammonia. I'm sorry. Yeah, here we go. Okay, better? All right, so we're going to interrelate these two guys, right? Okay, so we're going to interrelate 3 moles of hydrogen to 2 moles of ammonia. All right, so we're going to have moles of ammonia, and down here we're going to have moles of hydrogen. You can see, looking up here, it's going to be 3 to 2. All right, so I'll take my answer here, and let's see, multiply it here, and then divide it by that. Now, what I come up with is 12.3. Yeah, 12.3 moles of ammonia. Does everybody agree with that? Did everybody get that answer? Just to confirm it? Okay, good, good. Sometimes I'll hit a wrong key on my calculator in my rush, and don't do that. Don't make my mistakes. All right, so this is what we call like grams to moles, okay? And the heart of it, we still had mole to mole. But suppose the problem is set up where instead of saying how many moles of NH3, let's move the camera back here for a second. Let's go back and relive the beginnings here. How about how many grams of NH3 are produced? How many grams? Okay, well, let's just go back to what we've done here up till now and just put a tail end on it. Okay, let's come back here just a little bit. Okay, we produced 12.13 moles. Okay, so we want to go over here now and go to grams of NH3. Okay, so we have 12.3 moles of ammonia times, let's get a conversion factor up here. And what is my conversion factor for ammonia to get grams? What do I use? What do you use? Just tell us. What do you use? The molar mass, right, the molar mass, which is going to be 17, right? I'll just round it off to 17. Okay? So we're going to have 1 mole of ammonia, and up here we'll have 17 grams of ammonia. Like I said, I just rounded it off, but, it should be, what, 17.03, something like that. So let's take this and multiply it out. I'll put the answer down here. We can see moles of ammonia cancel out. And let's see, we got this and that times 17. And I come up with 208, and probably leave it at 208 grams of ammonia. What do you think? Okay? This is, in essence, the whole idea of the stoichiometry. Okay? If you're given moles and asked for moles, it's just a simple mole-to-mole conversion right out of the balanced equation. If you start with grams, you got to convert to moles and then get your answer for whatever form you need, moles or grams. But the important thing is you got to go through here. Now, I'd like to show you an example of something. I mean, some of you guys might feel like this is just superfluous, like we really shouldn't have to do it. But let's take this balanced chemical equation over here. Okay, start at the beginning. And instead of it being balanced in moles, let's balance it in grams, in mass. Okay? So if I have 3 hydrogens, I'm just going to kind of round it off to, we'll have 6 grams of hydrogen. Everybody okay with that? I'm just seeing what the number of moles are, and I'm multiplying it out by the molar mass. Okay, we have just 1 mole of nitrogen, okay, and that'll be, we'll call that 28 grams, okay, because each nitrogen molecule is 28. And then we have 3 moles of NH3, and that's going to be 17 times 3. That comes out to 51. I'm going to say 3, but 2. I'm sorry. I looked over there at the 3, and that confused me. Okay, so it's just 2 times 17. Okay, well, 2 times 17 is a little bit easier. 34. Thank you for catching me. 34 grams. Can we use that to go directly from mass to mass without going through mole-to-mole conversions? Let's see. Given 37.2 grams of H2, let's look at a whole new conversion factor now. We have grams of H2 down here, and we're going to have grams of NH3 up here. We're going to have 6 grams, 34 grams. Let's see what we get for an answer. Since I rounded these off just a little bit, it won't be exactly the same answer, but it should come very close. So if we have 37.2 times 34 divided by 6, there we go. Let's say I got 208. Well, I didn't round them off. I got 210. Okay. Which is pretty close. But, it should have been closer than that, actually. Let me recheck my numbers here. 37.2 times 34. Yeah, 34, okay. And then divide that by 6. Yeah, I get 210, not 208. So, like I said, I rounded some things off there, but anyway, you can see you can do it. In fact, when I did one in class the other day for another class, it came an awful lot closer than that. So if you guys see where I might have miscalculated something, tell me. But the thing is that if we balance chemical equations according to mass, which is pretty darn hard to do, we could go directly from mass to mass. But we don't do that. Okay, we balance chemical equations according to moles. Okay? So we have a 2 here. We'll have just a 1 here, right? And then a 3 here. Okay? Now, the reason I go through that little exercise is because some people still get confused when they're doing problems, and they think, given so many grams of that, they could just look at the molar ratios, the stoichiometric ratios, and just go directly from grams to grams. I was just trying to do that to kind of emphasize the fact that you always have to go back to moles. Any questions? Okay. Now, for this next part here, let's see. We have 208 grams of ammonia. Now, this did not come out of a laboratory. This came out of a piece of paper and a pencil and doing some calculations. Okay? This assumes a 100% yield, no problems, everything's going great. Textbook chemistry. Okay, this is called a theoretical yield. Okay, theoretical yield is 100% great. However, chemical reactions, never 100% yield. There's always that keeps you from getting to 100%. Okay? If you're, when you're doing organic chemistry someday, organic lab, when you make something in a pot, it doesn't mean that that's where you stop. You got to get that thing out of the pot, separate it out from the other, let's say, the other stuff, the other products, or maybe unreacted chemicals, whatever. You have to separate it out. It's called working it up. And you can lose quite a bit that way sometimes. You got to do filtrations, recrystallizations, whatever. Okay? As far as the chemistry itself goes, the longer a chemical reaction goes, the slower its reaction rate goes down. Okay? And if you think about it, I'll give you a little setup for something I'm going to be talking about in a few minutes. If you got A and B, the first thing that has to happen for A and B to make a product, which we'll call C, is that they have to collide. Now, there's some other things that have to happen too. But for the purpose of what I'm saying right now, let's just stop at the collision. Let's say for every collision, we get product. So we got a lot of A, a lot of B. They collide. They make product. We got a lot of product being made. But what happens is when you make the product, you start losing concentrations of A and B. So what happens when the concentrations of A and B go down, so do the rate, I'll say, of collision, okay, because there's fewer particles colliding. All right, so what will happen is you get like an asymptotic approach to, let's say, completion. One way you can fix that is going to be to put some extra stuff in there, some extra A or B, and that I'll talk about in a little while. But the point is this, is that just by that alone, you know, if you don't do something to goose it up a bit, you know, you're still not going to get 100%. Sometimes you might have decompositions, whatever. So the thing is, you have the theoretical yield. But let's say we took the 37.2 grams of hydrogen down to our laboratory and reacted it, and we ended up only getting, let's say, 185 grams of ammonia, and we'll say this will be from lab. Well, this is called the actual yield. Just 1 second, please. Thank you. For 1 second. That'll be the actual yield. Can I bring that down? Well, I should have moved it a long time ago. Okay, there you go. Oh, better late than never, right? I didn't make that up, by the way. Okay, so we got our theoretical yield up here that I've been talking about off camera. And down here, we take it to the laboratory, and we only get 185 grams of nitrogen, of ammonia. It's Friday. Okay, first of all, whenever we're talking about yields, yields are never given in moles. Yields are always given in grams or kilograms. But for what we're doing here, grams is probably very appropriate. Excuse me, I'm sorry. Still have it in there. All right, now, when you're reading chemical literature and they're doing synthesis, they'll always put at the end what your percent yield is. Okay, now the percent yield means in grams, and what it's based on is your theoretical yield versus what you actually got. So you can imagine a percent yield is going to look like this. We'll have percent yield is going to be your actual yield divided by your theoretical yield times 100. Yeah, we got how many minutes? 10 minutes. Hey, we got all kinds of time. People are already jumping ship. They probably see that iceberg. All right. So this is, in fact, let's do it real quick. You guys got your calculators. Shake your buddy next to you. Wake them up. Let's do this. So for the percent yield here, we'll have 185 grams of ammonia. And here we're going to have 208 grams of ammonia times 100. Now remember, units cancel out just like numbers. You have grams of ammonia over grams of ammonia. Well, guess what? Grams of ammonia cancel out because you got to always account for your units here. You know, keep that in mind. I'm sorry, excuse me. 208, and I come up with 88.9%. You can check my numbers to make sure they're okay, but I think they are. Okay, now the thing to remember is yields are always based on mass, and so when we talk about percent yields, it's always percent yield by mass, okay, not by moles or anything like that. All right, how are we doing? Okay, now to get to this next part, which will pretty much finish things up for us before the exam, let me give you a little introductory talk here. I'll leave the camera in there for right now. All right. We're going to be talking about limiting reactants, or limiting reagents, same thing. I'd like to start this lecture. People who took my prep chem, you'll be hearing it for the second time, so just sit back and don't give away the ending. Here's my formula for making a sandwich, and so I don't offend anybody's dietary needs or beliefs. I'll say we'll talk about maybe a cheese sandwich. 1 slice of cheese, 2 slices of bread. Is that okay? I'm trying to be very neutral now so I don't offend anybody, you know. Well, how about a bread sandwich? You had a piece of bread and 2 pieces of bread with it. You know? I'm not going there. We got a slice of ham. We have a slice of, I don't know what, cheese. Okay, everybody's happy. Slice of cheese. And it's synthetic cheese, okay? We have a slice of cheese and 2 slices of bread. Hey, that gives you 1 sandwich, right? Okay, that's your equation. Okay, so let's start making sandwiches. So if you have 4 slices of bread, 2 slices of cheese, we can make 2 sandwiches. You have to, don't be afraid. And if we have 4 slices of bread and 1 slice of cheese, we can make 1 sandwich. If you have 4 slices of cheese and 100 slices of bread, 4 sandwiches. You can see that all of a sudden we're kind of limiting how much stuff we can make. Okay? And if we have 2 slices of cheese and 100 slices of bread, all of a sudden the cheese becomes what we call the limiting reagent or limiting reactant. In other words, that's going to tell you how many sandwiches you can make. If you got 100 slices of cheese and 2 slices of bread, now the bread is telling you how many sandwiches you can make. Okay? Okay. In other words, we're talking about one of them being in excess, back to that term, and the other one we are now going to call the limiting reactant or limiting reagent, whichever you want to call it is fine with me. Okay? Now, how does this apply to chemistry? Well, I'll tell you. This is a kind of, they love to ask this problem, and I think it's just to kind of get you more and more into, you know, the comprehension, I think, of how things are reacting. Because the way we use this a lot of times, and if Dr. Godin, if you have some other thoughts on it, that'd be great. But as I told you, as the chemical reaction proceeds, we start losing reactants, okay, to products. Unless we have something called an equilibrium reaction, I'm not going there right now. We're saying everything goes from left to right, okay? Now, as we basically lose the number of reacting molecules, what we can do is we can put a little extra A in there or a little extra B in there. And what they will do is that excess they'll act as like scavengers. They can just get in there and try to get as many A's or B's as they can. So we will use an excess of one, and I'm not talking about a huge excess. We just put an excess in there to kind of push the reaction as far as we can. Does that sound all right? Just leaving it like that? I mean, there can be other things too. Thumbs up? Okay, you spared my life. Good. All right, now, the thing is, when you're writing a chemical reaction, you say, well, I'll put a pinch more of A in. Okay, you've done it. Okay, you know what you've done. But what they like to do is get in there and say, now, if I give you so many grams of this and so many grams of that, how many grams of product will you get? And it's actually kind of it's a fun game to get into chemistry, because then you got to figure out which one is the limiting reagent by how many grams I gave you. We got 5 minutes left. I'm going to get back to this guy here, and let's just set one up real quick. Okay, so give you something to think about and talk about all weekend, all right? Here we go. In fact, I'll just come over to here to do it. All right, let's see, come over to here, right about to here. That's good, right there. All right, so based on this chemical equation here for the production of ammonia, let's see, if I have, let's say 5 grams of hydrogen and 12 grams of ammonia, how many grams of ammonia, I'm sorry, 12 grams of nitrogen, how many grams of ammonia will be made? Okay? So the first thing we have to do is what? I'll give you the first word to the answer, convert. Convert grams into moles. Then we can look at our balanced equation and determine pretty easily which one is in excess and the one that is not in excess is the limiting reagent. Okay, the one that is excess is going to chew up all the limiting reagent, and you're going to have excess left over at the end. Okay, so if we have 5 grams of hydrogen, okay, it's H2, so that's going to be 2.02 grams of hydrogen over 1 mole of hydrogen. Grams of hydrogen cancel out, so it's going to be 2.02. We're only going to have like one significant figure there, so I'll tell you what, just to make it fun, let's say 5.0, just so we have 2 significant figures. So we get 5 divided by 2.02, and that's going to come out to 2.5 moles of hydrogen. Okay? Now we got 12 grams of nitrogen, so we're going to have 1 mole of nitrogen, and that's going to be 17 grams of nitrogen. What am I talking about? It's going to be 28 grams of nitrogen. Okay, so we're going to have 12 divided by 28. Whoa, hardly any there at all. 0.43 moles of nitrogen. Now, just looking at that, if we have 2.5 moles of hydrogen and 0.43 moles of nitrogen, just looking at the balanced equation, which one do you think is in excess? Well, you just check it out here. For every mole of nitrogen, we need 3 moles of hydrogen. So let's see. We have 0.43 moles of nitrogen. We only need 3 times that amount. So if we take this times 3, we're going to have 9, we're going to have 12. We only need 1.29 moles of hydrogen. I'll put down hydrogen needed. We have 2.5. We got twice the amount of hydrogen than we actually need. So what's the limiting reagent? You're right. This guy here is going to be our limiting reagent. Okay, now, on Monday, we'll take that and just finish the equation, finish the problem real quick. Okay? See you guys on Monday. Have a great weekend.
get